Hello, welcome back. All right, net ionic equations. Um, when you're doing a reaction in chemistry, the only things that we put into an equation are the things that actually change. So when you're running a reaction in a water environment, if the particles are ionized or dissociated, rather, if the particles are dissociated into ions as reactants, and then they wind up being the same ions as products, then we don't consider them part of the equation. So, for instance, when we did a reaction earlier in the year for the regular school year kids, not with the summer thing, but we had this reaction. We had lead nitrate, and we dissolved it in water. So I'm going to write AQ next to it. And we reacted it with potassium iodide, also dissolved in water. And then when we, okay, that's not working. Don't you move. All right, so that produced a yellow precip, lead iodide. And then later we were able to evaporate the water, but there was a dissolved salt in there, potassium nitrate. So I'm going to write AQ. It was dissolved into ions. So I'm going to go back and balance this real quick. Put a 2 out in front of there, and put a 2 out in front of there. So when something is ionized in water like this, it really doesn't exist as molecular lead nitrate. It exists as lead ions, and then it exists as nitrate ions separately. That's really what's happening inside the beaker. And same thing here with the potassium iodide. It was dissociated into ions. It wasn't a white solid anymore. And when we ran the reaction, we had that bright yellow solid that we filtered out. The summer kids, at least mine, will be doing this lab with me once we get back in the school session. And then that white solid wasn't a solid. When we filtered it, it was dissolved in the water environment. So it was really existing as ions. 2 moles of K plus, 2 moles of nitrate. So if you look at something like the potassium ions, they didn't change. So we're going to cancel them out of this equation. And the nitrate ions didn't change. We're going to cancel them out of the equation. There's something called spectator ions. They were there. They were required because they were part of the salt that you used. However, they're not part of the chemical reaction. They didn't change. What changed was the lead 2 plus ions, the iodide ions, and they became that yellow solid, lead iodide. So if we're really writing what happened, we should write lead 2 plus 2 moles of iodide produces lead 2 iodide solid. And what this says is 2 things. First, it identifies what's called the driving force of the reaction. Remember earlier we said that things like the production of water molecules, production of small covalent molecules such as carbon dioxide, redox reactions that produce more than 0.1 volts, combustion reactions, they all have strong driving forces, and the creation of a precipitate is one of those strong driving forces. So what the net ionic equation is actually doing is identifying the driving force here. And what it's saying is, look, you don't need lead nitrate to run this reaction. You just need a source of lead ions. So you could use lead acetate, and that would work. You don't need potassium iodide. Any soluble iodide compound, like sodium iodide, would work. Either way, the driving force is going to be the production of this yellow solid, this lead iodide. So again, the net ionic equation shows us what's actually happening in the reaction, and it shows us the driving force. And the truth of the matter is the molecular equation that we wrote back at the beginning of the course is false. It's not something that actually happens. All right, so for instance, this one, HCl plus NaOH, what is the net ionic equation? Well, the net ionic equation would identify the driving force of the reaction. And we said that acids and bases react to produce salts and water. So the production of the water molecule is the driving force. So in this case, the net ionic equation is H plus OH minus produces H2O. And there's a way the book teaches this, and as I'm going online, everybody else teaches it the same way, it seems, where you write the molecular equation first, and then you cancel out the spectator ions, and then you write your net equation. If you identify the driving force, and there's only going to be two on this last test, since it's an acid base and it's a water precipitation chapter, the only two driving forces we're going to have are the production of water molecules and the production of precipitates when we do KSP. So I would look to see what is the driving force of my reaction and then select the answer that has that driving force. Let me show you what I'm talking about with the things that I stole off the internet. All right, so here's our little equation right here, right? Hydrochloric acid plus sodium hydroxide produces sodium chloride plus water. Acid plus base produces salt plus water. Now, on the test, at the AP level, you would have to memorize which things are strong electrolytes, strong acids, strong bases, weak bases, soluble salts that ionize, and those that don't, in order to be able to do this. But I'm going to tell you on the test, because it's not required at this level for you to memorize that hydrochloric acid is a strong acid, and sodium hydroxide is a strong base. Sodium chloride is a strong electrolyte, which means it's a salt that breaks up into ions completely, and then water is a covalent molecule, so this is a weak electrolyte. Anytime you have a strong material, you're going to write it as ions in your net equation. If you have a weak electrolyte, a weak acid, weak base, then you're going to write it as a molecule. So when I see this reaction, and I said, all right, strong electrolyte produces sodium chloride plus water. What's the driving force? The driving force is the production of the water molecule. So all I need are the things that produce the water molecule, the H plus and the OH minus. And then if you look at the answer at the bottom, there you go. H plus OH minus produces H2O is the answer. Now, the way they teach it in the book is they say, all right, if it's strong, like hydrochloric acid, let's rewrite it as ions. Same thing with sodium hydroxide. Let's rewrite it as ions. Let's write our strong electrolyte, sodium chloride, as ions. And then let's go back and cancel out the spectators. So let's get rid of the chlorides. Let's get rid of the sodiums. And what we're left with is H plus, OH minus, H2O. I just think my way is a little quicker. Now, my way doesn't work very well when you get to the higher levels, but when you take AP Chem with me, I'll go through what adjustments you have to make in order to get it right. But for now, if you identify the strong driving force, you'll get through the problems a lot faster. Here's another example I stole offline. All right, sort of the same reaction I was talking about that we did in the lab, except for they used potassium chloride instead of potassium iodide. Again, they are taking lead nitrate, which is a strong electrolyte, and potassium chloride, strong electrolyte, and they're producing a solid, and potassium nitrate, which is a strong electrolyte. So we know that the driving force here is to produce the precipitate, lead chloride. What do we need to produce the lead chloride? We need lead ions and we need chloride ions. So they go through rewriting lead nitrate and potassium chloride and potassium nitrate, and then they go through and they cancel out their spectators, and then they're left with lead 2 plus 2 moles of Cl minus produces lead chloride. Again, identifying the driving force of the reaction. Okay, the same one from a third different source now. Strong electrolyte. How do I know at the AP level? I would know all nitrates are strong electrolytes. Group 1 metal ionic compounds are strong electrolytes. So there's another strong electrolyte, and there's my precipitate. So what's my driving force? Well, if I don't want to do it that way, I can write out all the ions like they did here, full ionic equation, and then cancel out the spectators. But I know that I need 2 moles of silver ions, I need chromate ions, and then that's going to produce my silver chromate solid. All right, so what type of questions would you get on the test? Glad you asked. As far as the precipitates, I just did 3 examples. I'm not going to do any more of those, but if we're looking at acid-base, there's really 2 types of acid-base reactions I'm going to give you. I'm going to give you a weak acid or base, and we're going to react it with a strong one to produce a salt and water. And the other type I would give you would be strong plus strong produces salt and water for our acid-base reactions. And I already did strong plus strong. If you're doing strong acid, you're doing strong acid, sorry. I mean, if you're using a strong acid, you would do H plus for the acid, and for the strong base, you would use OH minus, and then that is always going to produce H2O. And it doesn't matter which strong acid and which strong base combo you use, it always comes out to be that. For instance, if we were to use, let's use nitric acid, and we're going to react it with potassium hydroxide. Neutralization reaction. So we are going to switch the ions. So the H goes to the OH, and the potassium goes to the nitrate. So again, on the test, I would let you know that this is a strong electrolyte, this is a strong electrolyte, this is a strong electrolyte. So the nitrates are going to be written as ions and canceled out. The potassiums are written as ions and canceled out. What's left? H plus, OH minus, produces water. So anytime you get 2 strong materials together like that, strong acid, strong base, you're always going to get H plus plus OH minus produces H2O. Now, if one of the materials are weak, I give you a problem like this where I say, all right, we're going to do, I don't know, I'm going to make something up. Let's do oxalic acid. So we're going to do H2C2O4. Oxalic acid, I would, of course, give you the formula. I don't expect you to know oxalic acid at this stage, rather. And this is going to be a weak acid. And we're going to react it with potassium hydroxide, which is a strong base. And that's going to produce potassium oxalate, which is a strong electrolyte. And it's going to produce water. So I'm going to go back here and balance the equation. So we put 2 out in front of there. Okay. So you're doing this problem. You can rewrite it as ions, but you can't rewrite the oxalate as ions because it's a weak electrolyte. So what's the driving force here? Well, we got to be careful. Not everything's going to cancel out. So if you're dealing with a weak acid or a weak base, I'm going to advise that you follow their technique of, hey, let's write this thing out as ions. Can't write the weak acid as an ion because it's weak. Doesn't produce a lot of ions. But we can write the potassium hydroxide as ions. We can write the potassium oxalate as ions. And then, of course, we can't write the water molecules as ions because they are weak electrolytes. So what cancels here? The 2 potassiums cancel, and our net equation is oxalic acid plus hydroxide produces oxalate plus 2 moles of water. All right, so the only adjustment that you have to make here is if you're dealing with a weak acid. So what do the problems look like on the multiple choice? The problems would be, hey, the verbiage would be, what is the net ionic equation for the weak acid, oxalic acid, and then they give you the formula, the strong base, and then they give you the formula, producing the strong electrolyte and water, and then you have to go and select the net ionic equation from the list. Okay, second part of this video, writing KEQ for acids and bases and for things that dissolve. This is actually very easy because we did this in depth for the video that covered the end of chapter 22 before Le Chatelier's. So it's the same thing. It's going to be products over reactants that don't include any pure solids or pure liquids in the expression. Now, this thing right here, H3O plus, is something called hydronium. Whenever you see hydronium, treat it as though it's the same as H plus. And the thing here is that some chemists believe that when the H plus is donated to the water, it bonds and forms H3O plus. It does, but it's a very, very weak bond. And there have been scientists in the last 5 years that have argued that the bond isn't strong enough to technically say that H3O plus exists. It's really H plus plus H2O. So I will tell you that in your book it's H3O plus, and that in the college books I'm using it's H plus. So whenever we talk about H plus concentration for an acid or hydronium concentration for an acid, we're just going to go with it and accept both and consider that they are analogous to each other. Now, these K expressions, the ionization of an acid in equilibria we call Ka, the ionization of a base we call Kb, and the big thing about Ka and Kb is they are an expression of strength. The larger the Ka, the stronger the acid. The larger the Kb, the stronger the base. pH is not an indication of acid-base strength. pH is a measurement of the environment that you have. Again, for instance, hydrochloric acid is strong acid. But if you put 1 drop of hydrochloric acid in the ocean, it's not going to drop the ocean's pH to 1. All right, so they give you a problem like this. Hey, what's the Ka for this weak acid? And we're like, well, that's easy. We're going to do products over reactants. Our products are H3O plus and then X minus, and we're going to put that over HX. And of course, we get rid of the H2O because it remains pretty much constant, and we don't include pure liquids and pure solids in our expression. A couple of things I want you to know, though, some terminology. There are actually 2 forms of acid here. HX is what we call the molecular version of the acid. Molecular acid. The H plus or H3O plus is the ionized version of the acid. The X minus is the particle that HX becomes, so this is your conjugate base. So the formula for Ka is H plus times conjugate base over molecular acid. Same thing here for Kb. They want to know what the expression is. Okay, easy enough. Products over reactants. NH4 plus times OH minus over NH3. So again, some terminology. NH3 represents the molecular base. What do molecular bases become? They become NH4 plus, a conjugate acid. And then OH minus is your ionized base. So formula. Kb is conjugate acid times ionized base over based. I fell for that. Base over molecular base. All right, so let's try one real quick here. Okay, write the Ka expression for acetic acid. All right, so first of all, we have to know that acetic acid breaks up into H plus plus acetate. Now we can write our expression. Ka is ionized acid times conjugate base over molecular acid. Easy. Okay. Water solubility. When things produce ions by dissolving in water, we said that they are strong electrolytes, and when materials do not produce a lot of ions, they're weak electrolytes. And when we usually talk about solubility, when we're talking about ionic salts, we're talking about whether or not they break apart into dissociated ions. If it was a non-molecular organic substance, then our solubility and entropy would be a little different. We wouldn't really concern ourselves too much with ionization. But with salts, if it only produces a small amount of ions, we say it's insoluble. And when it produces a large amount of ions, we say it's soluble. Truth of the matter is, everything dissolves at least a little bit in water. Now, this equilibria expression we call KSP. It stands for the solubility product. Solubility product. And the reason why they call it product is because you wind up with the product of your positive and negative ions. And since we don't include pure solids in the expression, it gets left out, and there is no denominator. So we only consider ourselves with the numerator, which would be where the product is. All right, what is the general expression for KSP when lead 2 sulfate dissolves in water? Okay, first of all, lead 2 sulfate is not going to dissolve a lot, so this is a weak electrolyte, which means I'm going to use the double arrows. And again, we don't expect you to memorize which ones are weak and strong. We would let you know that. It's going to break up into lead and sulfate. Now, lead is found in two forms, positive 2 or positive 4. This has to be the positive 2 version because sulfate always has a negative 2 charge. Therefore, the lead has to have a positive 2 charge in order for the charges to add up to be 0. Now, lead sulfate's a pure solid. Ions are dissolved in water. So the KSP for this, we ignore the solid, and we just do lead 2 plus times sulfate. Easy. Okay, one last thing I'm going to throw in here real quick on this second to last video. What about calculations? Well, the calculations at your level, they're only going to have one thing in the water system. In other words, you're going to have a beaker with your slightly dissolved salt in it, or you're going to have a beaker with just the acid dissociating in it. It gets a lot more complicated when you start mixing in a lot of different chemicals, and we'll deal with that at the AP level. But for now, you might get something like this on a test. All right, suppose we know that the KSP for a certain salt is equal to 1.6 times 10 to the minus 14. And suppose the formula for that salt is A2B. All right, they want to know what is the concentration of B minus at equilibrium. Well, KSP gives you the equilibria for how much will actually dissolve. Now, in this reaction, or process rather, A2B will break up into 2 moles of A plus and 1 mole of B2 minus. All right, so if we write a KSP for this, we would say that KSP is equal to A plus squared times B negative 2 charge. Okay. Well, how much of this dissolves? Let's say 1 mole of B2 minus is created. How many moles of A plus would be created? Well, twice as much, 2 moles, right? And if 100 moles of B2 minus dissolved, then twice as much A would dissolve, 200 moles. I keep saying moles and I wrote molar. Okay, so let's say X amount of B dissolves. How much A plus would dissolve? Well, twice as much. Well, now we have enough information to go ahead and solve the problem, because here's what we can do. We can substitute in. We know that KSP is 1.6 times 10 to the minus 4. If we let A equal 2x and B equal x, then 1.6 times 10 to the minus 14 becomes 4x cubed, right? 4x squared on the first term times x, 4x cubed. So we can solve this. We say x cubed is equal to 1.6 times 10 to the minus 14 over 4. And then we can solve that in our calculator by taking the cube root, or raising this to the 1/3 power. So we're going to do what's inside the radical first. So 1.6 exponential negative 14 divided by 4, we get an answer. And now let's raise that. If you don't have a cube root function, I do on my calculator. If you don't, you could always raise this to the 1/3 power. I'm going to do the cube root. And x, which is equal to the B2 minus concentration, is equal to 1.6 times 10 to the minus 5 molar. Now, if that's the case, if they ask you, well, what is the concentration of A plus? Well, A plus is equal to 2x. So the concentration of A plus would be 3.2 times 10 to the minus 5. Right? So pretty easy. And when we discuss pH and pOH in the next section, I will show you an example of how to do a calculation with Ka and Kb. All right. Thank you very much. Second to last video. We're almost there.